When we discussed electric fields, we had two equations that we used. One we talked about directly, the other we just kind of developed along the way. But if we look at it in differential form, then the curl of the electric field is equal to 0. And if we use Stokes Theorem for this, it basically says that the integral around a contour of the electric field dot dl, electric field vector, direction vector, is equal to 0. Now, this electric field dot product with the differential length, and this is a contour, so it has a start and an end, and it basically is a loop, and this is a form of Kirchhoff's voltage law. Not a law. We didn't really talk about this too much, but it's a product of the discussion that we had later. Now, if we do the the divergence, it's not the dot product, apologize, it's the divergence of the electric field, we found that it was equal to our charge density over epsilon naught. And this is a volume, that's why we have a little v, right? It's charge in a volume. And we found that by taking the surface integral around, or the volume integral around both sides, that we came up with an integral for the electric field dot product with the differential area vector is equal to the amount of charge enclosed over epsilon naught. And we had this as Gauss's law. Well, it turns out that the magnetic field has similar types of equations. And so the first of those equations has to deal with the dot product, or the divergence, I'm sorry, I keep saying dot product, I mean the divergence. Divergence of the magnetic field is equal to 0, which means that there's no net flux, and this also means that there's no magnetic monopoles. And if we were to put this into an integral using the divergence theorem, then we would have that the surface integral of the magnetic field dot product of the area is equal to 0. And this makes sense because if I have a magnet and there's a magnetic field, then it doesn't matter what shape I put around this magnet, because if I put a shape here, then all the magnetic field lines that exit will enter on the other side. And if I put the box over here, then the same thing. The amount of magnetic field lines per area leaving is the exact same amount that enters, and so this integral is 0. Now the other property is the curl of the magnetic field is equal to this mu naught, which we will have to define, times J, where J is equal to the current density. And its units are amps per meter squared. So it's the amount of current going through a surface. And so if we use Stokes Theorem, well, what I want to do is integrate through a surface of my curl of the magnetic field, and that's going to be equal to the integral of the surface of mu naught times J. I should say differential J. And this just means if I take Stokes' theorem, then I get that the contour integral of my B vector dot dl vector is equal to, well, if I take the integral of my current per area, and actually this needs to be written like this, J d dA, then this integral turns out to be just the current that's enclosed with that shape, and this we term as Ampere's law. And it is the analog of Gauss's law. And so now we can define some relationships that will help us to be able to find magnetic field strengths much the same way as we did with Gauss's law. But just as Gauss's law was limited in use, so Ampere's law is limited in use. If we want to be able to have the analog to Coulomb's law, that's going to be what we have as Biot-Savart. So in this chapter, we're going to look at the magnetic field due to a straight wire. And the forces between two parallel wires. We'll look at Ampere's law. Solenoids. And toroids. And then Biot Savart. And the last topic will be hysteresis.